All right, good morning, everyone. I'm going to go ahead and get started. Okay, here we go. Okay, we'll start a new chapter today. Last time we looked at carboxylic acids, and next we're going to look at what are called functional derivatives of carboxylic acids. Okay, let me back up. Okay, we're going to focus on four classes of organic compounds, four different functional groups, and these are derived from carboxylic acids. Okay, these are the general formulas for these four functional groups. Okay, on the left we have acid chlorides, also called acyl chlorides. Next we have anhydrides. Okay, anhydrides are often mistaken for ketones or esters. Okay, but they're neither one. They are more reactive than both those functional groups. Okay, here we have an ester, and then we have an amide. Okay, notice that all of these they're derived from carboxylic acids. Okay, if we remove water from a carboxylic acid and something else, then we get these functional groups. Okay, first we'll look at acid chlorides. Okay, these consist of an acyl group. Okay, this is the acyl group right here. It's bonded to a halogen. By far, chlorides are the most common. Okay, here are a couple of examples. Okay, this one is ethanoyl chloride based on ethanoic acid, or acetyl chloride in the common nomenclature, based on acetic acid. And then here we have benzoyl chloride, okay, which is derived from benzoic acid. Okay, so to name these, we drop the IC acid, and then we add YL chloride. Okay, so benzoic acid becomes benzoyl chloride. Okay, these are examples of anhydrides. Anhydrides consist of two acyl groups bonded to an oxygen atom. Anhydrides may be symmetrical, okay, where we have two identical groups, or they can be mixed, where we have two different acyl groups. Right, to name anhydrides, we replace the word acid after the carboxylic acid and substitute anhydride. Okay, so this is acetic anhydride, or in the IUPAC it would be ethanoic anhydride. This is maleic anhydride. And then here's a mixed anhydride. This is acetic benzoic anhydride. Okay, acetic on this side, benzoic on this side. Okay, let me show you maleic acid. Right, this is maleic acid, and the common name specifically refers to the cis isomer. Okay, and so if we eliminate water, we close up the ring, then we have maleic anhydride. Okay, in the IUPAC, this would be butene dioic acid. Okay, we could say and it's cis. Okay, we could say 2-butene dioic acid, but there's only one place we can put the double bond. Okay, it turns out that the trans isomer is called fumaric acid. Okay, we can have other anhydrides besides those from carboxylic acids. Here we have a phosphoric anhydride from phosphoric acid. Diphosphoric acid is also called pyrophosphoric acid. Okay, we take 2 molecules of phosphoric acid, split out water, and connect these. Okay, deprotonate, if we remove all the protons, this is now the diphosphate or pyrophosphate ion. Okay, and then we can also have a triphosphate. Right, next we'll look at esters. The functional group of an ester is an acyl group bonded to an OR or OAR group. Okay, so we'll name the alkyl or aryl group first, that's bonded directly to the oxygen, followed by the name of the acid from which it is derived. And we'll change the suffix, IC acid, to ate. All right, so this is ethyl ethanoate or ethyl acetate. Okay, we have an ethyl group, which is bonded directly to the oxygen. And then the other part of the ester is derived from acetic or ethanoic acid. So that's where we get the second word, ethanoate or acetate. Okay, this one is diethyl butane dioate, or the common name for butane dioic acid is succinic acid. Okay, so commonly this would be diethyl succinate. Okay, you can have cyclic esters. These are called lactones. I think it's easier to use the IUPAC. A lot of these are still known by their common names. In the IUPAC, we name the parent carboxylic acid, and we drop the IC acid suffix, and we add lactone. Okay, the location of the oxygen atom on the carbon chain is commonly indicated by a Greek letter. Okay, so this is 4-butanol lactone or gamma. It's an example of a gamma lactone. Okay, gamma. Okay, this is the alpha position next after the carbonyl, then beta, and then when we open this up, this would be a carboxylic acid and alcohol. the ether oxygen here is on the gamma position. Right, phosphoric acids are very important in biochemistry. Phosphoric acid can form mono, di, and triesters. We name them by giving the name of the alkyl or aryl groups bonded to the oxygens, followed by the word phosphate. For more complex phosphate esters, it's common to name the organic molecules followed by phosphate. Okay, so this is dimethyl phosphate. We take phosphoric acid, we replace two of the hydrogens with methyl groups. That's where we get the dimethyl. And this last bullet point, here we have two examples. This is glucose, and this would be D-glucose 6-phosphate. And then this is pyridoxine, so this is pyridoxal phosphate. Right, let's look at amides next. The functional group of an amide is an acyl group bonded to a trivalent oxygen. We drop the IC acid from the name of the parent acid, and then we add amide. Okay, so remember the suffix for amide is amide. All right, if the amide nitrogen is bonded to an alkyl or aryl group, then we locate that group by showing its location on nitrogen by a capital N. Okay, it has to be a capital N. Right, so this is acetamide, okay, from acetic acid. It's a primary amide. The difference between an amine and an amide is the amine doesn't have this carbonyl group next to the nitrogen. Okay, here's an example of a secondary amide. Okay, so this is capital N methyl acetamide. Okay, to show that there's a methyl substituent on the nitrogen. Okay, and this is an example of a secondary amide. Nitrogen is directly bonded to two carbons. And then this is NN dimethyl formamide from formic acid. Okay, every substituent gets a number or a locant. And so we need both ends here. This is an example of a tertiary amide. Okay, this is abbreviated DMF. It's a common solvent. It's an aprotic solvent that's used in organic chemistry. All right. Earlier we talked about lactones. We can also cyclize amides to make lactams. Okay, so we name the parent carboxylic acid, drop the suffix, and then we add lactam. Okay, a 4-carbon ring, a 4-membered ring is called a beta-lactam. And okay, this is a 7-membered ring. It's called a epsilon lactam. This one on the right is an intermediate in the synthesis of nylon 6. Okay, the one on the left, okay, not specifically that compound, but the beta-lactam group, the 4-membered cyclic amide, is an important component of penicillin and cephalosporin type antibiotics. Okay, so here's a penicillin antibiotic called amoxicillin. And the different penicillins will contain different functional groups, here shaded in pink. And here is the beta-lactam ring. Okay, what happens here is a 4-membered ring is under strain. Okay, this carbonyl is electrophilic, so amino groups that are on the bacterial proteins will attack this carbonyl group, open up the ring, and this deactivates the enzyme that is used to synthesize bacterial cell walls. Right, of course, many bacteria have developed resistance to penicillin. They've developed the ability to produce enzymes which break down penicillin. And so one way of dealing with that is the drug manufacturers will add another enzyme which deactivates the enzyme which the bacteria use to break down the penicillin. So it's kind of an arms race that's going on. Okay, these are cephalosporins. Okay, notice the difference here. The penicillin type has a 5-membered ring, and then the cephalosporin has a 6-membered ring here with nitrogen and sulfur. And the different members of the family contain different functional groups at this location. This is one called Keyflex. Right, this is the dominant mechanism for carboxylic acid derivatives. Okay, and one thing that will help you narrow down the possibilities is that carboxylic acid derivatives are commonly either converted to carboxylic acids or to other derivatives. Okay, so in the general mechanism of nucleophilic acyl substitution, the nucleophile attacks the carbonyl. Carbonyl is polarized. Carbon end is plus. Nucleophile attacks the carbon nucleus, pushes a pair of electrons up onto the oxygen. It goes through this tetrahedral intermediate. The tetrahedral intermediate then collapses. Oxygen pushes down, and the original group there becomes the leaving group, and then we have a substitution product. All right, the reason that this doesn't happen in one step, like an SN2, okay, remember an SN2 has to be collinear. The leaving group and the incoming nucleophile have to be on a straight 180-degree path. Okay, well, the two-dimensional picture here doesn't show that the oxygen and the incoming nucleophile are actually 90 degrees apart from each other. They're perpendicular rather than collinear. And so that's why we have to go through this tetrahedral intermediate. Okay, in the general reaction in the previous screen, the nucleophile as shown was shown as an anion. You can also have nucleophiles that are neutral. Okay, and examples of neutral molecules include water, alcohols, ammonia, and amines. Okay, in the general reaction, we showed the leaving group as an anion to facilitate this important point. The weaker the base, the better the leaving group. Okay, and this is a key to the relative reactivities of carboxylic acid derivatives. Okay, so chloride is the best leaving group. Then carboxylate, the conjugate base of a carboxylic acid. Okay, then an alkoxide, and then an amide leaving group. Okay, where we have a nitrogen with a negative charge is actually not a very good leaving group at all. Right, so the halide ion is the weakest base. Okay, HCl is a strong acid, so therefore its conjugate base is weak. Therefore, acid halides are the most reactive toward nucleophilic acyl substitution. The amide ion is the strongest base and the poorest leaving group. Okay, and so therefore amides are the least reactive toward nucleophilic acyl substitution. Okay, so here's the order of increasing reactivity. Amides are the least reactive, then esters, then anhydrides, then acid halides. Right. Low molecular weight acid chlorides react rapidly with water to form a carboxylic acid and HCl. Higher molecular weight acid chlorides react less readily. Okay, so here we have acetyl chloride. Okay, and it will react just by adding water, and it produces carboxylic acid and HCl gas. Acetyl chloride is a liquid, and it will react with just water vapor in the air. And so if you open a bottle of acetyl chloride, it looks kind of scary because it looks like there's this smoke coming out of the bottle. And what that is, it's an aerosol mist of HCl. Acid chlorides are powerful lacrimators, which means they cause your eyes to burn and water. Right, anhydrides, as I mentioned, are more reactive than esters, but they are less reactive than acyl chlorides. Low molecular weight acid anhydrides react with water to give 2 molecules of carboxylic acid. And just like with acid chlorides, the higher molecular weight anhydrides also react with water, but less readily and less rapidly. Okay, so just exposing these to water, okay, over a period of time will cause hydrolysis. Okay, esters are hydrolyzed only very slowly. Okay, most of them are, even in boiling water. Hydrolysis becomes more rapid if they are heated either with aqueous acid or aqueous base. Okay, hydrolysis in aqueous acid is the reverse of the Fischer esterification. Okay, that was something we covered in the previous chapter, in which we combined a carboxylic acid and an alcohol to form an ester. We split out water, we formed an ester. Okay, so this is the reverse. Okay, this follows the same pattern. All right, water is the nucleophile. Okay, this is done with an acid catalyst. We go through this tetrahedral intermediate. Okay, so water attacks, we have a proton transfer. That's where we get the OH-OH. Okay, this one of these OHs becomes protonated, water leaves. I'm sorry, we're going the other way. The methanol gets protonated and methanol leaves. Okay, we split the ester into its carboxylic acid and alcohol components. Okay, if we add a proton, okay, and what's often done in either hydrolysis or formation of esters is we'll use a little bit of something like sulfuric acid For hydrolysis, it would be dilute sulfuric acid. Okay, so that increases the electrophilic character of the carbon atom. Okay. Right, so if we protonate this oxygen, okay, we have another resonance form in which the carbon would have the plus charge. So water can more readily attack the carbon. Right, the OCH3 then accepts a proton. Water removes this proton, oxygen pushes down, and it pushes out methanol. Okay, so H3O is regenerated, so it is a catalyst. Hydrolysis of an ester in aqueous base is often called saponification. Okay, so each mole of ester hydrolyzed requires 1 mole of base. Okay, and so for this reason, ester hydrolysis in aqueous solution is said to be base promoted rather than base catalyzed. Okay, notice also, again, we get the alcohol, but since it's in basic solution and carboxylic acids are acidic, we'll end up with the conjugate base of the carboxylic acid, or the carboxylate. Okay, so here is the base promoted hydrolysis of a methyl ester. Okay, so hydroxide attacks the carbonyl. Okay, a pair of electrons gets pushed up onto the oxygen. Okay, so that gives the oxygen a negative charge. We have a collapse of the tetrahedral intermediate. Okay, oxygen pushes down and it kicks out OCH3 minus. And then these two products undergo an acid-base reaction with each other. Okay, methanol is a weaker acid than the carboxylic acid, and so methoxide grabs this proton and we end up with the conjugate base of our carboxylic acid. Okay, the two main differences between acid catalyzed and base promoted ester hydrolysis are this. Okay, for acid catalyzed hydrolysis, acid is required in only catalytic amounts. For base promoted hydrolysis, equimolar amounts of ester and base are required. Secondly, hydrolysis of an ester in aqueous acid is reversible. Base promoted hydrolysis is irreversible because a carboxylate anion is not susceptible to nucleophilic attack. Okay, this is the carboxylate anion here. Okay, this is not susceptible to additional nucleophilic attack, so the reaction stops there. All right, since amides are less reactive, since nitrogen anions are poorer leaving groups than the other leaving groups that we talked about, the hydrolysis of an amide requires much more vigorous conditions than does hydrolysis of an ester. Hydrolysis in aqueous acid requires 1 mole of acid for each mole of amide. Okay, in contrast to esters where we only had to use a catalytic amount. The products are a carboxylic acid and an ammonium salt. Okay, in our chapter on amines, remember amines are bases. So that means the ammonia that's produced is going to react with the acid to form an ammonium salt. Okay, in basic solution, hydrolysis of an amide requires 1 mole of base per mole of amide. The products are a carboxylate salt and an amine. Okay, so here we have N-phenyl ethanamide, or N-phenyl, or also called acetanilide. Okay, when this is hydrolyzed in base, we get the conjugate base of the acetic acid, sodium acetate, and then we get aniline. Right, so here's a summary of the rankings of reactivity. Okay, acid chlorides are up at the top, then we have anhydrides, and we have esters, and then we have amides. Right, so acid chlorides and anhydrides can be hydrolyzed with just water. Esters and amides require either acid or base to hydrolyze them. Okay, so besides converting carboxylic acid functional derivatives into carboxylic acids, okay, the other category of reaction that we'll look at is converting carboxylic acid derivatives into other derivatives. Right, so acid chlorides can react with alcohols and phenols to give an ester and HCl. Okay, so if we split out HCl and we reconnect these, we get an ester. Okay, so this one is called cyclohexyl butanoate from butanoic acid. Acid anhydrides can react with alcohols to give 1 mole of ester and 1 mole of a carboxylic acid. Okay, so here we have acetic anhydride reacting with ethanol. And the two products are the ester, ethyl acetate, and then the byproduct is acetic acid. Right, here is the reaction involved in the synthesis of aspirin. Okay, if we take 2-hydroxybenzoic acid or salicylic acid, and we react it with acetic anhydride, okay, the phenol group gets esterified, and this becomes acetyl salicylic acid. Okay, the carboxylic acid takes priority in naming, and then acetic acid is the byproduct. Okay, acetyl salicylic acid is aspirin. Okay, esters can also undergo an exchange reaction called trans-esterification. Okay, this is acid catalyzed, and the original OR group is exchanged for a new OR group. Okay, so here we have two equivalents of methyl benzoate reacting with 1,2-ethane diol with a little bit of acid catalyst, and that forms the diester of ethylene glycol. Okay, and then it releases 2 molecules of methanol from the methyl ester. Okay, this does require a large excess of the alcohol with the new OR group. Okay, because it is an equilibrium reaction. All right, and I might also mention this is a very slow reaction. You have to heat it at reflux for often several hours in order to get the product. Okay, amides do not react with alcohols under any conditions. Right here we have the reaction of NH3 and amines with acid halides. Okay, acid halides will react with ammonia, primary and secondary amines to form amides. Okay, they won't react with tertiary amines because you have to have at least one hydrogen on the nitrogen to start with. Okay, you have to have 2 moles of amine, or you have to have some other base present per mole of acid chloride. 1 mole to form the amide and 1 mole to neutralize the HCl. Okay, so hexanoyl chloride can react with 2 moles of ammonia. It forms hexanamide and ammonium chloride. Anhydrides react with ammonia, primary and secondary amines to form amides, just like acid chlorides do. Again, we need 2 moles of ammonia or amine, or we have to have some other base present. Okay, 1 mole to form the amide and 1 mole to neutralize the carboxylic acid byproduct. Okay, so here acetic anhydride plus 2 ammonias gives acetamide and ammonium acetate. Okay, remember the ranking. We had acid chlorides, anhydrides, esters, and amides. Okay, so you can convert those derivatives that are higher up on the chart to those that are lower down. Okay, the last 2 are the esters and amides. Esters can react with ammonia and amines to form amides. They are less reactive toward ammonia and amines than either acid halides or anhydrides. Okay, so this often requires a high temperature and a long time in order to get this reaction to go. Okay, and then amides will not react with ammonia, secondary or primary amines. Okay, so acyl chlorides react with ammonia to form amides, and hydrides also react with ammonia to form amides. So do esters, but much more slowly, but amides are the least reactive. Okay, so we can interconvert derivatives into other derivatives. All right, so acid chlorides can be converted into any of the other 3 derivatives and to carboxylate salts. Anhydrides likewise can be converted to esters, amides, or carboxylates. Carboxylates can be converted back to carboxylic acids by adding strong acid, okay, something like HCl. And then carboxylic acids can be converted to acid chlorides using something like thionyl chloride, SOCl2. Esters will also react with Grignard reagents. The difference here between the reaction of Grignard reagents with aldehydes and ketones versus esters is that with ketones and aldehydes, it's a 1-to-1 stoichiometry. But with esters, 2 equivalents of Grignard reagent will react. Okay, so here we have a formate ester, methyl formate, and it reacts with 2 equivalents of Grignard reagent. And okay, the R comes from the Grignard reagent, so we've added 2 of these R groups, and we get a secondary alcohol from a formate ester. Okay, from any other ester, again, we add 2 equivalents of Grignard and we get a tertiary alcohol with at least two of the alkyl groups the same. Okay, so this starts out just the same as the reaction of a Grignard with an aldehyde or ketone. Okay, the carbonyl is polarized, the carbon end is plus, nucleophile attacks the carbon nucleus. Then we get this tetrahedral intermediate. Okay, and the reason why this doesn't get protonated to the alcohol at this stage is that if you think back a few chapters ago, we talked about something called hemiacetals, where we had an alcohol and an ether on the same carbon. Most of those are not stable. Okay, so this hemiacetal anion collapses. Oxygen pushes down and kicks out OCH3 minus, and we get a ketone. The ketone is then subject to attack by the second equivalent of Grignard. And then when we hydrolyze that, when we add dilute acid, okay, oxygen picks up a proton and we get a tertiary alcohol. Right, esters are reduced by lithium aluminum hydride to 2 alcohols, and at least one of them is always a primary alcohol. Okay, the alcohol derived from the carbonyl group is always primary. The other alcohol will depend on what this R group is. Okay, so it's going to split it. This carbonyl will get reduced to the alcohol, and then when we're all done, OCH3 becomes CH3OH. Okay, so we get 2 alcohols when we reduce an ester with lithium aluminum hydride. Okay, this has to be carried out in 2 steps. Okay, we have to wait until the first reaction is done before we add the water and the acid. Sodium borohydride, while it reduces aldehydes and ketones, does not reduce esters. Okay, so here we have a ketoester. Sodium borohydride only affects the ester, and it doesn't touch, it only affects the ketone, it doesn't affect the ester. Right, amides are reduced to amines. Okay, notice that here the oxygen is completely gone in the product. This also requires lithium aluminum hydride. Okay, so the CO double bond is converted to CH2. All right, here's a summary of interconversions. And I'm going to go ahead and stop there. And I will see you on Monday.